In this video, we will try to learn about Kuhn Tucker conditions. This question was asked by a friend, Monteir Almonteir. I'm not able to pronounce the name correctly, so I'm really sorry for that, brother. So, what is the Kuhn Tucker condition? What is its relevance in economics? So, we will try to learn about that. Okay. First, we know that if we have the optimization problem, let us say we have to optimize. If we have the optimization problem, there can be two possibilities. Optimization problem can be anything. We want to maximize our utility or minimize our cost. And if we have optimization problem and we have equality constraints, that means if we have or if we want to optimize a function and we have equality constraints, we can use either the Jacobian method or Lagrange's method. Okay, Lagrange's method. But what does this mean? Optimization can be we want to maximize our utility, okay, or which is equal to, let us say it is a function of two goods, okay, subject to our equality constraint. Means we have a budget constraint, let us say p of x times x plus p of y times y is equal to m. That is our budget. Okay, so if we want to optimize our utility function, in this case maximize our utility function, we have the equality constraint here, we use Lagrange's method, multiplier method or Jacobian method to solve this very optimization problem. But if we have inequality constraints, let us say we have, I will write here inequality constraints, then we use this Kuhn Tucker condition, that is K, I'm not able to write the spelling correctly, Kuhn Kuhn Tucker method. Okay, so I hope you got the idea why do we use Kuhn Tucker conditions. When we have optimization problem and we are dealing with inequality constraints, we use the Kuhn Tucker method. Okay, and it can be like this. We want to maximize our utility function. Let us say we have a function subject to the inequality constraint. We don't have the equality constraint. If it was the equality constraint, we can easily use the Lagrange's method. Okay, so let us say we have g x y is less or equal to 0, and we have another budget, what we can say constraint, that is inequality constraint. Let us say xy is less or equal to 0. I'm just writing it randomly. Okay, so in this case when we have the inequality constraints, we use the Kuhn Tucker condition. Okay, I hope you got the idea why do we use the Kuhn Tucker condition or why we use the Lagrange's method. Okay, one more important thing is to be remembered. Whenever we solve the Kuhn Tucker method, we need the Lagrange's method in solving this Kuhn Tucker condition. Okay, so let me rub this out and coming to back to our topic, that is Kuhn Tucker condition. Okay, so I will give you an example how do we use the Kuhn Tucker condition. Okay, now how do we use, there are some steps in solving the Kuhn Tucker condition. Okay, so I will give you an example and I will then try to give an algorithm how do we use that very condition. Okay, first I will give you an example and it will make more sense for you. Okay, let us say we want to maximize our utility. We are given a utility function u is equal to xy. Okay, that can be our satisfaction or happiness, that is how much happiness we get when we consume x and y commodities. Okay, this is our utility function. Also we have a budget constraint here, that is x plus y is less or equal to 50. Okay, how do you interpret it? That means the price of good x is 1, the price of good y is also 1, and we have a budget of 50 and we want to consume both goods x and y, and we should consume such way that it should not exceed our budget. It should be either equal to 50 or less than 50. Okay, this is the meaning of this first constraint. Let us say this is called the income constraint. I will write here, this is our income constraint. Okay, after that we have another constraint here. Let us say we have 2x plus y is less than 60. Okay, how do you interpret? Let us say this is our coupon constraint. Coupon constraint. Now it says us that we need coupons coupons to purchase 1 unit of x and 1 coupon for the purchasing 1 unit of good y, and total number of coupons available for us are 60. And how do we interpret it in the real life example? It can be used in case of, let us say, in case of wartime rationing. When there is war, the government wants to ration the essential commodities, and in that case the government can issue coupons to the consumers. Okay, so this is our coupon constraint, and this is our budget constraint for a consumer. Okay, so this is how do we try to uh, make sense of these two constraints. This is our income constraint. Okay, so the consumer is $50, let us say, and second is 60 coupons. Government is providing 60 coupons for a consumer to buy good x and y, and individual has $50 to buy good x and y, and one good costs 2 coupons because 2 is the price, and here one good of y costs 1 coupon for the consumer. A total number of coupons available for a person are 60. Okay, so we just want to maximize, let us say, I will write here, we want to maximize our utility subject to that very two constraints. One is the income constraint and another is coupon constraint. Okay, now how do we solve this? First of all, we need to form the Lagrange's function. Okay, and I have shown you in n number of videos how do we form the Lagrange's function. So I will not show here because of the lack of the space. I will just write. So let us say L denotes our Lagrange's function is equal to. So Lagrange's function is formed by, we add the objective function, that is xy, okay, plus we solve. So I will just try to make it more sense to show you how do we form the Lagrange method. Okay, if we have x plus y is equal to 50, I will write here, let us say x plus y is equal to 50. First condition is, I'm just ignoring this inequality sign. First we write it like this: 50 transposing all terms on RHS, so this is 50 minus x minus y, okay, is equal to 0. Okay, then we multiply it by lambda 1. Okay, this is how do we form the first constraint. Okay, so we have lambda 1 50 minus x minus y. Okay, this is our Lagrange's function with first constraint, plus similarly we can form another constraint. Okay, so this is 2x plus y, ignoring this sign for making sense here, is equal to 6, and we can write 60 minus 2x minus y is equal to 0. Okay, and after that we multiply it by lambda 2. Okay, so this is how do we form the Lagrange's function. I have shown you in various videos how do we solve it, how do we form the Lagrange method, Lagrange's function. So I'm just skipping some steps here. Okay, so we have another constraint, let us say lambda 2, this is 60 minus 2x minus y. Okay, this is our Lagrange's function. Now what are the Kuhn Tucker conditions? So I will write here, Kuhn Tucker condition is there, Kuhn Tucker conditions require, Kuhn Tucker conditions require here that our Lx Lx, that is the partial derivative of this Lagrange's function with respect to x. What will be the partial derivative of this Lagrange's function with respect to x? So differentiating with respect to x. Okay, so the derivative of x is 1 here, so we are left with y. Okay, since x is here, the derivative of x is 1, so this is minus 1 into lambda, that is minus lambda 1. Since no sorry, here is x involved, so the derivative of x is here 1, so we have minus 2 here. Okay, so we have minus 2 lambda, minus 2 lambda. Here the Kuhn Tucker condition says that this partial derivative of Lagrange's function should be less or equal to 0. Okay, also our x should be greater than 0. Okay, then this will make any sense. So having 0, having negative units of a good does not make any sense here. Okay, sorry. And also another condition is that x times this Lagrange's function with respect to x should be equal to 0. Okay, so I hope I am making sense here. Similarly for ly, that means partially differentiating our Lagrange's function with respect to y will give us, so I will not try to explain. So here the derivative of y will be 1, so we are left with x. Okay, the derivative of y is 1 here. Okay, so we have minus 1 here, minus 1 into lambda is minus lambda 1. Derivative of y is minus 1 here, y is 1, so we have minus 1 into lambda 2, that is minus lambda 2. It should be greater than 0. Y should be also greater than 0, obviously, then it will make sense. And y times L of y should be equal to 0. Okay, similarly we have another condition, that is L times lambda 1. That means partially differentiating this Lagrange's function with respect to lambda 1. What will we get here? If we, since no lambda 1 is involved in the first term and in the last term, then we are left with the derivative of lambda 1 is 1, so we are left with 50 minus x minus y. Okay, and it should be greater than 0. Okay, that is lambda 1 should be greater than 0 for maximum here. Okay, and also this lambda 1 times L lambda 1 should be equal to 0. Similarly we have L lambda 2 differentiating this Lagrange's function with respect to lambda 2 this time, so the derivative of lambda 2 is 1, so we are left with 60 minus 2x minus y. It should be also greater than 0. Okay, that means lambda 2 should be also greater than 0, which means lambda 2 times L lambda 2 should be equal to 0. Okay, these are the conditions. Actually, I'm not saying lambda 2 L lambda 2 will imply by from this, so I'm just saying these are the conditions for Kuhn Tucker. Okay, now so we got these very things. Now comes the trial and error method. We will use trial and error method in solving what will happen to our utility and inequality constants here. Okay, now first we assume that, let us say, let me use another color here. We assume first, we assume that lambda 2 is equal to 0. Lambda 2 is equal to 0. Okay, and lambda 1 is greater than 0. So what does this mean? It simply means that first we assume that we ignore first our coupon constraint. We don't care about our coupons. Okay, so we ignore this coupon constraint. Okay, this condition is satisfied when lambda 2 is equal to 0. Okay, so we care only about the money constraint. Okay, that means lambda 2 is equal to 0, lambda 1 greater than 0, means ignoring the coupon constraint and solving by the Lagrange's multiplier method. Or we say that this lambda 2 is equal to 0, that means constraint 2 is non-binding. So constraint constraint second is non-binding. Okay, so what will happen? I am just giving you the steps. First step is we assume the second constraint is equal to 0, or what we say that we ignore this coupon constraint and we only care about the income constraint. Okay, so we assume that we don't run short of the coupons, and we solve for the budget constraint. Okay, so what will happen then? Now if we assume this very thing, okay, what will happen then? Now we have to use this we have to use these very conditions in solving for the Lagrange's multiplier method. Here you can see if x into lambda x is equal to 0, x into lx is equal to 0. Here if we transpose x here on RHS, so x 0 divided by x will be 0. That means our lx is equal to 0. Here also ly is equal to 0. Here also l lambda 1 is equal to 0, and here L lambda 2 is equal to 0. Okay, if we assume lambda 2 is equal to 0, lambda 1 is greater than 0, then we solve this by Lagrange's problem. Okay, now that means Lx is equal to 0. That means what is Lx? Lx is this very thing. Okay, and it is equal to 0. I am not able to show here because I have no space left for this very thing. If we assume Lx is equal to 0, that means this thing is 0, and also we assume lambda 2 is equal to 0. So actually it is here lambda 2. Okay, so in place of lambda 2 we have 0. So what will be our Lx? So I will write here our Lx will become y minus lambda 1, since we have assumed x2 is equal to 0, so it will be equal to 0, and we have set it equal to 0. Okay, is equal to 0. Then what is ly means this very thing, so this is x minus lambda 1, since lambda 2 is 0, and we set this ly is equal to 0. I will write here 0. And what is l lambda 1? L lambda 1 will mean this very thing, 50 minus x minus y is equal to 0, and we don't use the lambda 2 because we have assumed that lambda 2 is equal to 0. Okay, I am very sorry for the background noise. I am not able to control them, so be it. Okay, now we got the three equations and we have three unknowns, so let us try to solve. Okay, y minus lambda 1 is equal to 0 implies y is equal to lambda 1. Okay, here also x minus lambda 1 is equal to 0 means x is equal to lambda 1. Okay, now if y is equal to lambda 1, x is equal to lambda 1, doesn't this mean that y is equal to x? Okay, if y is equal to x, we just plug this y is equal to x in this equation to get the value of x or y. Okay, so just plug y is equal to x here, so we have 50 minus 50 minus, in place of x we have x, in place of y we have also x is equal to 0, and we have 50 minus 2x is equal to 0, or 2x is equal to 50, or x is equal to 50 upon 2, which comes out to be 25. Okay, we got the value of x is equal to 25, and I will rub it, okay, to save the space, which implies we got x is equal to 25. Okay, when we got x is equal to 25, we again put the value of x is equal to 25 in this equation. So what will we get? We get 50 minus, in place of x we have 25, minus y is equal to 0, which implies y is equal to 50 minus 25 is equal to 25. Okay, so we got x is equal to 25, y is equal to 25. We got the optimal values for good x and good y. Okay, so everything's okay up to this. Now since we have assumed lambda 2 is equal to 0, that is constraint 2 is non-binding. Okay, we just need to verify whether it was correct or not. Okay, what does this mean? We simply want to put the value of x is equal to 25, y is equal to 25 in the second constraint, and to make sure it is not being violated. Okay, so what will we do? We just put x is equal to 25 and y is equal to 25 to make sure that our assumption was right, that lambda 2 is equal to 0, that we don't care about the coupons. So our coupon was not violated. Coupon condition was what? Coupon condition was not violated. Okay, so if we take this coupon condition, that is to test, we have 2x plus y should be less than or equal to 60. Now what we got, the value of x was 25, so 2 into 25 plus 25 should be less or equal to 60. Okay, so this is 225 is 50 plus 25 should be less or equal to 60, but it is 75 is not equal to or less than 60. That means this condition was violated when we assumed lambda 2 is equal to 0, or when we say that coupons are not the issue for us. Okay, I hope I am making sense here. So first we assume that lambda 2 is equal to 0, and we solved for by the Lagrange method. After that we got the optimal values of x is equal to 25, y is equal to 25. Now we were to test whether our assumption was correct, that is whether this constraint was not actually violated. And when we put x is equal to 25, y is equal to 25 in our second constraint, that is coupon constraint, we see actually it was violated. Okay, so what will we do? So we will say our assumption was false. Okay, so I will write we did a false assumption. Our assumption was false. Okay, now what will we do then? Since the second constraint was not satisfied, then this time we will assume, I will write here, I will assume here, let us say lambda 1 is equal to 0, lambda 2 is greater than 0. Okay, that means in this case we are ignoring this income constraint. Okay, we say lambda 1 is equal to 0, that means it is non-binding here. Okay, so I'm just ignoring the income constraint here. Okay, I am saying money is not issue for us for time being. Okay, if we assume this very thing, let us use the Lagrange's method again. Okay, so this is our condition number step 2. Okay, since step 1 was failed, bound to be failed, then we use the step 2. In this case we assume lambda 1 is equal to 0 and lambda 2 is greater than 0. Okay, now wherever we have lambda 1 is equal to 0, we will see here, so we have Lx is equal to, now we have lambda 1 is equal to 0, so what we are being left with, we have y minus 2 lambda 2. Since we have equated it to 0, whole this partial derivative with respect to x, so this is equal to 0. Similarly we have L of y. Now L of y is x minus lambda 2, because lambda 1 is equal to 0 we have assumed here. Okay, so we are left with x minus lambda 2 is equal to 0, and another condition should be L of lambda 2. What is L of lambda 2? We have this very thing, that is 60 minus 2x minus y. Okay, and it should be equal to 0. Now we need to solve this. Okay, let me rub this out to make space here. Now if y minus lambda 2 is equal to, so I will write here, I have the space here. Okay, so from this equation what will we get? We get here y is equal to 2 lambda 2, which implies lambda 2 is equal to lambda 2 is equal to y upon 2. Okay, from this condition what will we get? We get x is equal to lambda 2. Okay, now if x is equal to lambda 2 is equal to y upon 2, which implies x is equal to y upon 2. Okay, so we use this very relation and put this very relation in our this constant, that is L lambda 2. Okay, if we put here, so what will we get? That is 60 minus, in place of x, so I will write 2. In place of x we have y upon 2 minus y is equal to 0. Okay, so this 2 and 2 will get cancelled, so we have 60 minus 2y is equal to 0, or 2y is equal to 60 implies y uh, is equal to 60 upon 2, which gives us 30. That means we got y is equal to 30. Okay, if we got y is equal to 30, we just need to plug y is equal to 30 back again in this very equation. So we have 60 I am writing here now, 60 minus 2x minus, in place of y we have 30 is equal to 0, which will give us so 60 minus 30 is 30. So if we transpose this, which implies 2x is equal to 30, which implies x is equal to 30 upon 2, which gives us 15. Okay, so optimal value of x is 15. So we got two values here, the optimal conditions, that is x is equal to 15, y is equal to 30. Now we just need to check whether our assumption was correct, that we don't ignore, we don't care about our income constraint. Okay, for that we need to put y is equal to 30, x is equal to 15 back in our constraint first. Okay, to make sure that our assumption was right. That means our x plus y should be less or equal to 50. Okay, now what is the value of x? It is 15. What is the value of 30 y? That is 30. It is less than 0, less than 50 there, because 30 plus 15 is 45, is actually less than 50. Okay, that means our assumption was correct. Okay, true. Now what does this mean? When the value of x was 50, y was 30, both the constraints are satisfied. Okay, or I can say that none of the constraint is violated, because we got x plus y is less than 50. Here I have shown. Also we got 2x plus y less or equal to 60. Okay, if we plug we have 2 in place of x, we have 15 plus y is 30. We can see that 2 into 15 is 30, plus 30 is actually equal to 60. Okay, so we say here that we got our optimal results, and by these we can see that this condition is also satisfied. X is greater than 0, we are getting the positive values of our commodities. Y is greater than 0. Okay, also we can see lambda 1 will be greater than 0 if you can solve, since where can I say, since lambda 1 is equal to y, and we got y is equal to 30, that means lambda 1 is also greater than 0. Lambda 2 should be greater than 0 also. So where can we see, where is our lambda 2? Lambda 2 is y upon 2. So what is y? Y is 30. Now lambda 2 will be 30 upon 2, 30 upon 2, which is equal to 15. That means this is also satisfied. Okay, and these things are also satisfied. If you just plug the value of x, y, and lambda 1, lambda 2, you can see that these very conditions are satisfied. Okay, so by this we mean that our optimal values will be, what will be, we got the optimal values, that is x is equal to 15, y is equal to where is y? I'm just lost through my eyesight. That is y is equal to 30. Okay, And what is the certification or utility that the consumer got? U is equal to x into y, that is equal to, what is x? X is 15, y is 30. So what is this? This is 0. 3 5s are 15, 3 1s are 3, is equal to 4. That means we got the certification level are 450 and none of the constraint is violated. With that, I wind up this video. So there can be another case when both lambda 1 is equal to 0, lambda 2 is equal to 0. If we were not able to satisfy both the constraints, okay, when we take lambda 1 is equal to 0, lambda 2 is greater than 0, then we would have to go for the third step. Third step would have been that lambda 1 is equal to 0 and lambda 2 is equal to 0, and then we can use the algebraic method. We cannot use the Lagrange. We can use the Lagrange's method, but it would have been more suitable if we use simply the basic algebraic method in solving for the optimal values of x and y. Okay, so step 3 will be only when this very what you call this very condition was not satisfied. If step 2 failed, then we could have gone to the step 3 when we will where we would have assumed lambda 1 is equal to 0, lambda 2 is equal to 0. That means we would have got that y is equal to 0 and x is equal to 0, and it will not make any sense here. If x is equal to 0 and y is equal to 0, that means the consumer will not get any certification. Okay, so I'm just trying to say you, if first step 1 and step 2 failed, then we could have used the third step, that is lambda 1 is equal to 0, lambda 2 is equal to 0, and then checking our constraint functions. Okay, I hope I make myself clear in this video. If you like these videos, please share and subscribe. This is the only motivation that gives me morale, that boosts me to make more useful stuff for you people. It is simply a free course for you people. I'm not um, even hiding anything from you. Whatever I can do, I am just using my knowledge of mathematics and a little bit of economics to make myself useful for you people. Okay, so only motivation that makes me going is if you share, subscribe this channel, okay, so that I can continue. Thank you.